Our job now is to have a quick whistle-stop tour around the loop of Henle on our way to figuring out exactly how it is that the loop creates urine that is concentrated. Some things that we've got to know, and they are that just do color change. The descending limb of the loop of Henle, okay, the descending limb of the loop of Henle, and I'm doing it in blue, is permeable to water. Okay, permeable to water. So what this means is that water can move out of the descending limb of the loop of Henle into the interstitium, where it gets picked up by the vasorecta. Okay, then the vasorecta are created from the efferent arteriole, and it forms a capillary structure, and it goes around the loop of Henle, and it does this in a particular type of nephron, which is called a juxtamedullary nephron. You've got two different types of nephrons. You've got cortical nephrons and you've got juxtamedullary nephrons. The cortical nephrons are in the cortex of the kidney, and the juxtamedullary nephrons start in the cortex, but everything below the proximal convoluted tubule dips down into the medulla. Roughly 85, you've got an 85, sort of 25% split between cortical and juxtamedullary nephrons. Now, the descending limb of the loop of Henle is permeable to water. The ascending limb of the loop of Henle is not. It is not permeable to water, but what it does have right throughout are specialized transporters. I'll just draw them in here, like this. Now if we zoom in over on this side to what the ascending limb of the loop of Henle will look like, where you've got a transporter, it'll kind of be something like this. You've got the transporter in here. Okay, so this is the ascending limb here, this is the transporter. These transporters are called Na plus K plus 2Cl minus co-transporters. So it should come as no surprise to you to know that what they transport are sodium, potassium, 2 chlorides. But what they do have is a potassium leakage channel. So what will happen is, as the fluid is coming up this way like this, sodium will go through, chloride, 2 of them will go through, and you'll get a potassium that goes into here and then leaks back out and goes up there, like that. So it'll move out and then it'll just leak, because potassium does that. It's like a naughty little toddler. Key thing here is that antidiuretic hormone makes these things just go nuts. It really increases the ability of these guys to work. So in times of water deprivation, what we end up getting is salt moving this way like this, while water comes this way. Okay, let's have a look at how this works. So what I've done is I've drawn over here some very rudimentary loops of Henle. So it's helpful if we consider what happens in 3 steps. So what happens when we get flow of tubular fluid, what happens when the ascending limb pumps, and then what happens because of basically the law of physiology in the kidney, which is the water follows salt. So we'll call this one move water. So we already said that we're in water deprivation, which means that we've got tubular fluid coming through here at 300 milliosmoles. Okay, this tubular fluid will flow through 300 milliosmoles. It'll flow around you, it'll be 300 milliosmoles, and it'll flow up the ascending limb 300 milliosmoles into the distal convoluted tubule. But over here we have got the sodium, potassium, 2 chloride co-transporters. So what's going to happen here, we've still got 300 milliosmoles coming down here, and we've still got that down the bottom here. But what happens as we come around this hairpin bend is that we start to come into contact with the transporters. So what's going to happen is that we're going to pump salt out. The effect of which is going to be that we're taking salt, in other words, we're taking stuff out of the fluid that is coming up here. So as we come into contact with these co-transporters, we dilute what is left behind because we move salt out into the interstitium. So what that does is it concentrates the interstitium. In other words, it raises its osmolality. Okay, leaving behind more dilute fluid. Then we've got water. Water is going to follow salt, so it's going to move this way because the interstitium has become more concentrated. Okay, so water is going to kind of move to try and balance this out. So the interstitium was more concentrated, like that. Water is, we've got tubular fluid coming in at 300 milliosmoles, it's flowing down here, and then the water in the tubular fluid is moving out, so it's getting more concentrated. It's going to end up matching what is down here. Okay? Alright, now let's draw these guys in again. What we've got is, this situation. We've still got 300 milliosmoles coming in. Okay, so now we're just adding to the flow again. 300 here. But we've already concentrated what was at the bottom. So we've still got this here. Okay. That's still flowing. Okay, so we're still 400 here. But we've got the last remnants of the more dilute stuff from here. Okay. So that's the flow. We've still got the pumps are still working. What are they going to do? They're going to go ahead and do their job. Okay, so we're going to pump salt out all the way up here. So what's the effect that this is going to have? Okay, so we've got 400 down here. We've got 300 still coming in. We've still got 300 in the middle. And we've got flow like this. We're going to pump some salt. What's that going to do? It's going to dilute what's here. So we're going to go down from 400, call it down to 300. Okay, so we're going to concentrate what's there. We've taken 100 out, so we put 100 in. So we're now creating a 500 milliosmoles concentration down in the interstitium. This 300 is going to still get pumped and pumped and pumped and pumped and pumped, and we'll call it, I don't know, say 150 at the top like that. So we've got a gradient starting from 400 down to 350 here. Okay, 500 pump, 500 there, down to 350 there. And then the next thing that's going to happen is water is going to do what it does, and it's going to follow the salt again. So what do we end up with? Well, we've still got flow coming in. That's still going to be 300 at the top, but water is now going to start to equilibrate. So as it comes down to the bottom, the water is going to move this way, and what's it going to do? It's going to concentrate whatever is left behind. 500 there, we've still now got 300 here, we've still got the gradient down to 150 here, and this keeps going on and on and on. So tubular fluid flows in, we pump salt, and then water equilibrates. The end result, guys, is a gigantic salty gradient. And if we just clear. So the end result, guys, is a gigantic, big fat, salty gradient from the top of the loop of Henle. We get start down to, we'll put it about here. Let's just say, draw a line through like that. From 300 milliosmoles because of the pumping of salt and the equilibration of water, down as far as 1,200 milliosmoles down the bottom. So 500 in the middle, 700, 900, down to about 1,200, all the way down like that. So basically what we're doing, because antidiuretic hormone, right, let's talk about what he does. Antidiuretic hormone is going to make sure that these guys go mental and they're going to start pumping salt like crazy. But the other thing that antidiuretic hormone does is it puts a channel into, I'll change color, into this guy, the collecting duct. Okay? It's going to put a channel in that's going to allow water to work its way out. And this is called an aquaporin type 2 channel. Now this is important because these channels here are also, that allow water out, they're also aquaporin channels. They are aquaporin type 1 channels. So antidiuretic hormone does two things. It ramps up the salt pumping and it causes aquaporin channels to appear in the collecting duct. Now what we're doing is we're creating a salty gradient from 300 down to 1,200 milliosmoles, and we're passing the collecting duct through that salty gradient and chucking a load of channels into the walls that allow water to move out. So when water in this tubular fluid is passing down through this collecting duct, it is following the salt, because where salt goes, water goes. So that means the water is moving out, 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 which is concentrating the renal tubular fluid, which is becoming urine as it goes through here. And what is left at the bottom is a small quantity of concentrated urine. This water goes out into the interstitium, it gets picked up by the vasorector, which eventually finds its way back into the right-hand side of the heart. This has got implications for a lot of things. It has got an implication for your plasma osmolality, but the plasma osmolality has got an implication on your blood volume. So this mechanism is part of BP control. Why? Because the kidney's awesome. Anyway, I hope that you found this instructive. I hope that you found it interesting. Please, 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 please like, comment, subscribe. Let me know that what I'm doing is making a difference. Thanks, guys.